We flip a switch, a light comes on. We press a button, a motor starts spinning. We do it every day. But what's actually going on inside those wires? Well, it turns out there are these incredible, invisible forces at play. Today, we're going to pull back the curtain on two of electricity's most powerful and useful hidden secrets.
Okay, picture this. You're walking around a science fair. You see this little model crane, but instead of a hook, it's just got an iron nail wrapped up in some wire. A student flips a switch, and boom, the nail suddenly acts like a magnet, lifting a whole bunch of paper clips. Then she flips the switch off, and they all just drop. There's no normal magnet anywhere, just a battery and a coil of wire. So what on earth is going on?
This is the big mystery we're going to solve together. How can a simple flow of electricity create the invisible force of magnetism, literally out of thin air? To get to the bottom of this, we've got to rewind the clock a bit and uncover a fundamental secret about how electricity and magnetism are related, a connection that for a long time totally baffled scientists. So, way back in 1820, a scientist named Hans Christian Ørsted basically stumbled upon this secret with a really simple setup. He just placed a wire over a compass. With the power off, no big deal, the compass needle pointed north, just like it's supposed to. But the second he flipped that switch and current started flowing through the wire, the needle twitched. It jumped to the side. This was the first real proof that electricity and magnetism aren't separate things, they're deeply connected. So here's the bottom line. Anytime an electric current is moving through a wire, it generates its very own magnetic field. It's just a basic rule of the universe. And when that current stops, the magnetic field just vanishes. This whole phenomenon has a name, the magnetic effect of electric current. Okay, Ørsted's discovery was really cool, a great aha moment. But the real magic happens when we figure out how to control and amplify this effect. Let's see how we turn this scientific curiosity into a genuine superpower. So, if a boring old straight wire creates a tiny magnetic field, what happens if we get a bit more creative? Can we actually harness this thing to build a powerful magnet anytime we want one?
Oh, you bet we can. If you take that wire and wrap it into a tight coil, all the little magnetic fields from each loop add up, and the whole thing gets stronger. But here's the real game changer. You stick a piece of iron, like that nail from the science fair, right in the middle. The iron core basically supercharges the magnetic field, concentrating all that force. And just like that, you've built a powerful, controllable magnet we call an electromagnet. And that science fair project, it was way more than just a toy. This exact principle is working all around us. We're talking giant electromagnets lifting cars in scrapyards, sorting metals in recycling plants, and they are the absolute heart of the electric motors that power everything from your desk fan to electric vehicles. But here's the best part, the thing that makes them so useful. Unlike a regular magnet you stick on your fridge, an electromagnet's power is completely adjustable. If you need it to be stronger, you just pump more electric current through it or add more loops of wire. And, of course, the most important thing, you can turn it on and off with the flick of a switch. So, magnetism is this incredible side effect of electricity. But it's not the only one. Nope. There's another equally important power hidden in that current. And this is one you've definitely felt before. Think about it. If you've ever messed around with a simple circuit, maybe even building that little electromagnet, you might have noticed the wires getting a little warm. Well, that's not an accident. That is the clue to electricity's second secret power. Think of electricity flowing through a wire, kind of like water flowing through a pipe. If the pipe is really narrow, the water has to struggle to get through, right? It faces opposition or resistance. The same exact thing happens with electricity. As the current pushes its way through a wire, that resistance turns some of that electrical energy into heat. And that's it. The heating effect of electric current. Now, not all materials are created equal here. A copper wire, for example, has really low resistance. It's like a super wide open pipe. That's why we use it for wiring. Electricity flows through it easily without it getting too hot. But then you have a material like nichrome wire, which has super high resistance. It puts up a huge fight against the current, and in doing so, it gets incredibly hot. And you know what? Sometimes that heat is exactly what we want. This effect is the secret behind so many appliances we use every single day. The glowing red coils in your room heater or your toaster, that's just a high-resistance wire, designed perfectly to turn electricity into useful heat. So we have magnetism and we have heat.
both cooked up by a simple electric current. But where does that current even come from in the first place, especially when you're not plugged into a wall? Well, the answer is usually sitting right there in your hands. The very first battery, called a voltaic cell, was a thing of beautiful simplicity. You just take two different metals, say copper and zinc, and you stick them in a conductive liquid, an electrolyte. A chemical reaction kicks off, and it starts pushing electrons from one metal to the other, creating an electric current. It's basically a tiny chemical power plant in a jar. Of course, carrying around sloshing jars of acid isn't exactly practical, is it? The really big innovation was the dry cell battery. It replaced that messy liquid with a thick, moist paste. This one simple change is what made batteries portable, convenient, and safe enough to use in all our gadgets. From there, batteries just kept getting better. You've got your single-use batteries that work until their internal chemistry is all used up. But then you have rechargeable batteries, like the ones in our phones and laptops. They're designed so that the chemical reaction can actually be reversed just by plugging them in, which lets us use them over and over again. And this journey is far from over. Right now, scientists are working on the next giant leap, solid-state batteries. These get rid of the liquid or paste electrolyte altogether and use a solid material instead. The promise? Batteries that are safer, charge way faster, and hold a lot more power. They're going to be essential for the future of electric cars and all our portable tech. So, from a twitching compass needle to a wire that gets warm to the touch, we've seen how a simple flow of electrons creates these powerful magnetic and thermal effects that literally shape our modern world. It really makes you wonder, if these massive forces were hidden in plain sight for so long, what other connections, what other invisible powers are still out there, just waiting for the next curious person to find them?